Hi everybody, today we are going to talk about linear programming. So linear programming is essentially finding optimal solutions when you have an objective function and a constraint. So essentially you're going to be given two things. You're going to be given an objective function, which you're not actually going to be graphing. You're going to use this to decide what your minimum or maximum value is. And then you're going to be given a system of constraints, which are going to be inequalities. So first you're going to graph the system of inequalities and find your solution set. Then you're going to find the coordinates of all of the vertices of your bounded area. Then you're going to take each of those coordinates and you're going to evaluate them within your objective function. So you're pretty much going to substitute the x and y values from each of the coordinates to see which one gives you either the biggest number for a maximum or the smallest number for a minimum. So typically, objective functions will be something like a profit function. So you'll want to find the maximum value, or maybe it'll be like a cost function. So you'd want to find the minimum value. So the optimal solutions for the objective function will always occur at one of the vertices. Unless you have an unbounded region, in which case you might not have an optimal solution. But if it does exist, it will occur at one of the vertices. Okay, so we're going to start with this problem. We have our objective function, which is z equals 3x plus 2y. So we want to find the x and y values that make z the largest. However, x and y have to fit into this set of constraints. So the first thing we're going to do is we're going to graph the system of constraints. So it's really important for these that you find some way to keep your different functions organized, because when you graph them, you'll want to be able to quickly match it with the correct function. So I'm going to use colors to do that, but maybe you want to label A, B, C, D, but just find some way to keep it organized. So for these types of problems, you're typically going to see that x is greater than or equal to 0 and y is greater than or equal to 0. So we're just working in quadrant 1. And for these actually as well, the way to graph the linear equations, probably the most efficient way, is actually just to graph the x and y intercepts and then connect, because really those are going to be important points most of the time. And it doesn't really matter how accurate our graph is in terms of like the slope. You just want to know where things are crossing. So for our red function, if x is 0, y is 2. So that's going to be our y-intercept. And if y is 0, x is 4. So we have 4, 0. Then for our blue function, if y is 0, x is 1. And you can see that our y-intercept would actually be -1. So we actually have a graph. If you put it into slope-intercept form, you have y is greater than x plus 1. So it is just a slope. It has a positive slope, so you get a graph that looks something like this. And like I said, it doesn't need to be accurate. All you need to know is that it has a positive slope. Now from here, we need to figure out where to shade. So this graph would be everything below your line, because it says y is less than. But this graph, actually, if you moved y to the other side, it'd be everything above your blue line. So it's everything below your red, above the y, to the right of your y-axis, and above your x-axis. So it's going to be this region right here. Okay, so now we need to make sure we know all of the coordinates of your bounded region. So this is going to be one of our coordinates as well. And we already have two other ones, so we know these three, but we still need to find this coordinate. So here we can see that we're actually going to be solving the system of the red and the blue equations. So I'm going to use my blue equation, and I'm going to solve for x. I'm going to use substitution here. I'm going to substitute that into our red equation. So y plus 1 plus 2y equals 4, 3y equals 3, so y is equal to 1. And if you substitute that back into blue, you get x equals 2. So this coordinate is at 2, 1. So these are our 4 potential options for maximizing our objective function. So now what I'm going to need to do is I'm actually going to need to go in and substitute all 4 of them into our objective function to see which one gives us the largest or the maximum output. So even though we know that probably 0, 0 is not going to be our maximum, we still need to check it. Sorry, this should be 2y. And you do need to show that you are checking each one. Then we could say, let's check the point 0, 2, and we get 4. Let's check the point 1, 0, and we get 3. And then let's check the point 2, 1, and we get 8. So you can see here that our maximum value is going to be 8, and that is going to occur when x equals 2 and y equals 1. So the maximum is 8, and it occurs when x is 2 and y is 1. All right, so go ahead and pause the video and give this problem a try. Okay, so here you can see that I've graphed the system of inequalities, and I have 3 coordinates that could be optimal values. So I substituted all 3 into the objective function, and I saw that the maximum value is 30, and that occurs when x is 0 and y is 6. Okay, let's try another one. So here you can see that we actually have 4 linear functions in addition to our axes, so we're going to have to be really careful to keep our work organized. So I'm going to color code again. This is going to be my red, blue, green, and yellow. And once again, we're really just working in quadrant 1, which is very common for these types of problems. So for our red function, if x is 0, y is 2, and if y is 0, x is 3. Okay, for our blue function, if x is 0, y is negative 15, and if y is 0, x is 5. So here's our x-intercept, and then we just have something with a positive slope, so it's just going to go up from here, kind of like this. For our green function, if x is 0, y is 4. And if y is 0, x is negative 4. So you see we actually have a positive slope. We have y equals x plus 4. So this is just going to be a graph that's going up again. It doesn't need to be super accurate, but you do need to know that it is going up. And then for our yellow function, when x is 0, y is a little bit more than 5, so it's somewhere up here. It's actually 27/5. And when y is 0, x is 27/2, so it's going to be somewhere way over here, something like this. So when we find our overlapping shaded area, we can tell that in this case, it would be y is greater than, so we're going to shade above the red line. And here we would actually move y to this side, so it says y is greater than. So we shade above the red and above the blue. This one says y is less than, and this one also says y is less than, so we're going to shade below and below. So that means the overlapping region would be in here. Okay, so we can see for this, we already have some of the coordinates of the vertices, but we have to find these two. So this is where a really good example of why we need to keep our work organized. When I see that I want to find this coordinate, I can clearly see that I need to solve using the green and the yellow. So if I had to go and I wouldn't be able to tell which equation goes with which line, that would be a huge problem. So I can clearly see which 2 equations I'll be using. So I'll start with my green equation, and I'll use substitution. So I'll say y equals x plus 4, and I'm going to substitute that into the yellow equation. So we can say 2x plus 5 times x plus 4 equals 27. Then we have 7x equals 7, giving us x equals 1. And then you can substitute that back into green, and you get y equals 5. So this coordinate is at 1, 5. And then for this other coordinate, I can clearly see that it's going to occur where the blue and the yellow are intersecting. So I'm going to start with my blue equation and solve for y. I'm going to use substitution again. And I'm going to substitute that into the yellow equation. And then if I start solving here, we get 7x equals 102. So x equals 6, and then you can substitute that back into the blue, and you get y equals 3. So this coordinate is at 6, 3. So now I have 6 different values that I need to check to find the minimum value of our objective function. So I'm going to zoom in a little bit over here. So once again, our objective function is z equals 5x plus 7y. So I do need to substitute all of them. So it might just take a little bit of time, but it is important to do. So we'll start with 0, 2, and we get 14. And then we can do 0, 4, and we get 28. Let's check 1, 5. And here we would get 40. Let's check 6, 3. And we get 51. And then we can check 5, 0. And we get 25. And last one, and we get 15. So here, if you look at the problem, they're asking you to find the minimum value. So we can see here that our minimum value is 14. And that occurs when x is 0 and y is 2. But we could also use this to find our maximum value, if that's what we were asked to find. So we could see that our maximum value is 51, and that occurs when x is 6 and y is 3. All right, so go ahead and pause the video and see if you can find the maximum value of this function. All right, let's have a look at your work here. So you can see that I graphed the 3 functions. So I have my red function, my blue function, and my yellow function. Here's the solution set. So here I have 5 coordinates. And you could see that I found this coordinate using the red and the blue function, so I solved for that here. And I found this coordinate using the yellow and the red function, so I solved for that here. And then I substituted all 5 values into the objective function, and that showed me that the maximum value is 880, and that occurs when x is 60 and y is 20. All right, so now I just want to talk about a few interesting cases. So one is when you have multiple optimal values. So you can see here, this has already been graphed for us, and they actually already found the coordinates for us. So if you have this objective function, and let's say you go in and you check the coordinates you have to maximize it. So let's do that. So we have 2 times 0 plus 2 times 0 equals 0. And then we have 2 times 4, or 0 plus 2 times 4 equals 8. Then we have 2 times 2 plus 2 times 4 is 12. And then 2 times 5 plus 2 times 1, well, it's actually also 12. And then checking our last one, 2 times 5 plus 2 times 0 is 10. So you can see in this case, we actually have 2 coordinates where we have a maximum value of 12. And actually the interesting thing is if you use the linear equation between your two coordinates that give you that maximum value, any point on that segment is going to be your maximum value. So here, while the maximum is occurring at one of your vertices, it has two, and it's actually also occurring at the line that connects those two vertices. So it's kind of something to look out for and just to know that it is possible. Okay, the last type of interesting case I want to talk about is when you have an unbounded region. So here they want us to find the maximum value for this objective function when x is greater than or equal to 0, y is greater than or equal to 0, and having the following constraints. So we're going to start by graphing our constraints. So I'm going to do red, blue, and green. Okay, so for our red function, when y is 0, x is 4, and when x is 0, y is 2. For our blue function, when x is 0, y is 7. And here's 0, 7. And when y is 0, x is 7/3, so somewhere around here. Okay, and for our green function, when x is 0, y is 7/2. And when y is 0, x is -7. So actually this is just an equation that has a positive slope. So it's going to go off in this direction. Now, if you look at where our shading should occur, it's going to be everything above the red line, everything above the blue line, and everything below the green line. So it's actually going to be an unbounded region that looks like this. So we still need to check to see if we can find a maximum value, and if it does exist, it will occur at one of our vertices. So we know one of them for our region, but we still need to find these two. So for the first one, I can clearly see that we need to solve the system between the blue and the green. So I'll start with the green equation, and I will solve for x. I can say x equals 2y minus 7, and I can substitute that into blue. So 3 times 2y minus 7 plus y equals 7. So here we'll have 7y equals 28, so y equals 4, and then if you substitute that back in, you get x equals 1. And then to find this coordinate, I can see that we need to solve the system between blue and red. So I'm going to start with our red equation, and I'm going to solve for x. And I'm going to substitute that into blue. So here, if I start combining like terms, we have negative 5y equals -5. So y will equal 1. And if we substitute that back into the original equation, we get x equals 2. So this coordinate occurs at 2, 1. So now I need to go through and I need to check those 3 coordinates in our objective function. So here, if you actually look at the graph, we can tell that since our region is unbounded and it's actually going in the positive direction, all of these values up here will give you a higher maximum value. However, there's no way to determine a single set maximum value. So in this case, there's no maximum, but there will be a minimum. So we're going to plug those in to our objective function. And we're going to figure out what our minimum value is. So here we will have 12, here we will have 10, and here we will have 16. So we can see that our minimum value will occur at will be 10, and that occurs when x is 2 and y is 1. So you kind of have to look at your graph and use a little bit of logic whenever you have an unbounded region. All right, so go ahead and pause the video and give this one a try. So you can see the way that this one is unbounded, we have no maximum, but we do have a minimum, which will be 30, and that occurs when x is 10 and y is 0. All right, that's all for today. Thank you for watching.